Well, then why have we got a problem?
Put up chart number 4, please.
You need this small segment called the tunnel segment if you're not going into Space Lab. Go to chart 2489A.
These men and women are doing the impossible. They are creating humankind's very first reusable extraterrestrial spaceship.
And what, you can cut the interface here, and you don't need anything downstream.
Well, then why can't I go EVA, too, with 5
You can go out here. Let's go to chart number 7, please. What the alternative?
There will be no prefabricated parts, no instruction book. Every element of the project is brand new, poised on the cutting edge of science and imagination.
You are go for orbit, go for orbit.
It had always been NASA's intent to create a method of transporting men and materials between Earth and the heavens. But the project accelerated after the conclusion of the Apollo moon missions in the early 1970s. In many ways, the technology behind a space shuttle is more sophisticated than a lunar expedition. In both concept and completion, it is an unprecedented human achievement, designed to rocket into Earth orbit at a height of 350 miles, carry up to 7 people and 65,000 pounds of freight, perform delicate missions in zero gravity, then land back on the planet's surface like a glider and be prepared to repeat the trip 100 times over. The first practical challenge of the endeavor concerns the vehicle's ability to withstand the 2,500-degree heat of re-entry. When the Apollo astronauts returned from the moon, their command module was protected from incineration by a heat shield of asbestos resin, which burned up upon re-entry. But the shuttle shield must not burn away. Instead, a remarkable new insulating material was developed which can be used on up to 100 excursions to space and back. With the weight and consistency of styrofoam, it is manufactured from an easily obtainable source, sand. The heat-dissipating properties of the shuttle's insulation is so efficient, it can be handled while still red hot. The shuttle's 34,000 insulation tiles must be individually milled and fitted to their unique place on the vehicle, covering the ship's aluminum skin, which would otherwise melt at a mere 320 degrees. This requires that each tile have its own code number, which relates to the specific place and curvature of the area for which it was cut, then sprayed with a polymer to avoid absorbing moisture and weight between flights. Like parts of a jigsaw puzzle, shuttle components from contractors across the country flow into the California assembly facility of Rockwell International. This wing section has come from Long Island. Wheel and brake assemblies from Ohio. Flight control system from Florida. Payload bay doors from Oklahoma. And crew living quarters from Colorado. From all across the United States, people have worked at solving the shuttle's construction challenges. From special robotic welding to using lasers to precisely cut insulation from around electrical wiring. There are 4 separate propulsion systems on the shuttle. Twin rocket boosters support the orbiter and the external tank on the launch pad and supply most of the thrust for blastoff and the first 2 minutes of flight. The main propulsion system, a cluster of 3 liquid propellant rocket engines supplied with liquid oxygen and liquid hydrogen from the external tank. The orbital maneuvering system, 2 pods mounted on the aft, producing propulsion for the final stage of ascent, maneuvering in space, and retrofiring for descent. The reaction control system, comprised of 44 small rockets mounted in clusters in the nose section and in the 2 rear pods, which align the shuttle while in orbit. solid rocket boosters are the largest of their kind ever built, 150 feet long, 12 feet in diameter, assembled from 4 segments of 1/2-inch steel. The solid propellant inside the casing looks and feels like the hard rubber of a typewriter eraser. After ignition, the boosters will be up to full operating pressure in less than 1 second, with a combined thrust of nearly 3 million pounds. The 3 main engines can swivel 21 degrees up and down in the vertical position and 17 degrees from side to side to steer the vehicle during flight. The liquid hydrogen and oxygen use a propellant stored in the external tank, a structure just over 150 feet long with a diameter of 28 feet, constructed of aluminum alloy up to 2 inches thick. It is actually 2 propellant tanks connected by a cylindrical collar called an inner tank. The forward tank holds 140,000 gallons of liquid oxygen at -297 degrees Fahrenheit. The aft tank holds 380,000 gallons of liquid hydrogen at -420 degrees. Before assembling the final craft, 45 tests at 6 different facilities were performed to make certain the propulsion system operated perfectly.